This is section 12-2 where you're finding limits algebraically, and that means not using a calculator. So when you try to evaluate it and you plug in the number the limit's approaching and you get 0 over 0, you're going to try one of these three methods, either factoring, foiling, or getting a common denominator. So you may need to pause this. I'm going to go right into the example. Pause it to write down what I've written here, but I'm going to go on. So first example that I have is finding the limit as x approaches -1. And so it's going to be of x squared plus x all over x plus 1. And you'll notice that if you plug in -1 into here and then also here and here, you'll end up getting -1 squared minus 1 all over -1 plus 1, or 0 over 0, which obviously is a problem. So that's when you want to try one of the three methods. So since there's an x in common, I'm going to take out an x, and I'm left with x plus 1. And I have a common factor that can actually cancel and simplify. So now I can just plug in the value of the limit, -1. So I end up just getting -1 for the limit. Alright, in my next example, I'm going to have you find the limit as h approaches 0 of 4 plus h squared minus 16 all over h. So again, you try plugging in 0. This is the first thing you always want to try. And you notice right off the bat you get 4 squared minus 16 over 0, or 0 over 0, which you can't have. So then you try option 2. Now there's nothing to factor, but you can try foiling because of this squared right here. So I'm going to try multiplying 4 plus h times 4 plus h. And if you can FOIL that out in your head, that's even better. But I'll show you what you do. So you do the 16, and then you get a 4h and another 4h, or 8h, and then you have plus h squared when you FOIL the last part out. So then you can simplify. The 16s end up canceling. What else ends up canceling is this h can cancel with each of those. Since I had an h in both of them, I could cancel 1. So this expression simplifies into 8 plus h. Now you're able to plug in your limit. So you end up getting the limit as 8. Alright, and the last example that I have for you here, I'm going to have you find the limit as h approaches 0 again. And I'm going to have you do 1 over h plus 2 minus 1/2 all over h. So there's nothing to factor, there's nothing to FOIL, but I do have two expressions in the numerator, and this is where you probably want to use the idea of common denominator. So I have an h plus 2 and a 2. So this one's missing the h plus 2, and this one's missing the 2. So I'm going to multiply this by 2 over 2, and it's going to be the whole thing. This is a 2. It kind of got lost in the writing, 2. Alright, so now you have a common denominator to actually simplify. So this is still all going to be over h. Here I'm going to have the 2 and the h plus 2 that's common. And on the top, when I distribute this out, I'm going to get the 2 and then minus, and I'm going to distribute this -1 right here to the whole thing. So I get minus h, so let me write this, minus h minus 2, because the -1 needs to be distributed out. So then stuff is going to simplify. The 2's end up canceling in the numerator. So I'm going to move right down here. And I end up with -h over 2 times h plus 2, all divided by h. So I have a fraction within a fraction, and to get rid of this, I can multiply by 1 over h. 1 over h. This ends up canceling. These h's end up canceling. So I'm left with on the top -1 over 2 times h plus 2. At this point, there's no more simplifying, so you're going to try to plug in your limit again. So I'm going to try plugging in my limit. I'm going to try 0, and I'm not going to get 0 over 0 like I would have had I not done this. So I end up getting negative 1 over 2 times 0 plus 2, or I end up getting negative 1/4 as the limit. Okay, so in this next portion, if you ever have a square root, you're going to need to use the following technique to simplify if you don't have a calculator to evaluate the limit. So you can go ahead and pause this if you need to write down what I've written. I'm going to go right into the example. So rationalizing. So here's an example. I have the limit as x approaches 0 of the square root of x squared plus 9 and then minus 3 all over x squared. So if you try to plug in 0 as is, so I try to put 0 into here and into there, I'm going to end up getting 0 over 0. So whenever you get to have a square root, what you're going to need to do is you're going to need to rationalize. So in this case, since the root's in the numerator, you're going to rationalize the numerator. So you're going to multiply the top and bottom by the exact same thing. You're multiplying by a 1. But what you're going to do when you rationalize is this number changes. So if it's plus, then it becomes, or if it's minus, it becomes plus here. And if it was minus, it would be plus. Or if it was plus, it'd be minus. So I'm going to multiply both the top and bottom by the same thing that's in the numerator. The only difference is that you're going to take opposite of this sign right here to rationalize. Alright, so basically this becomes a problem of just foiling everything out. It's how well can you FOIL. So when you FOIL this thing out, multiplying like roots, the roots cancel. So you end up getting x squared plus 9. The roots are gone. Here, I'm going to get 3 of these roots, and then I'm going to get minus 3 of those exact same roots. Those are going to cancel. That's the point of rationalizing. And the last product will be minus 9. And this is all over x squared times the square root of x squared plus 9 plus 3. So you'll notice conveniently that the 9's cancel, and then the x squareds will also cancel. So I'm basically left with 1 in the numerator, and then I have the square root of x squared plus 9 plus 3. So now at this point, I'm going to try to plug in 0 to see if I can actually calculate the limit now. So when I plug in 0, I get 1 over the square root of 0 squared plus 9 plus 3. And I just basically get the square root of 9, which is 3. So I get 1 over 3 plus the 3 here. This plus 3 is in the denominator. So I get the limit as 1/6. So if you need to go back and see how I foiled the first, the outer and the inner ended up canceling, and then the negative 9. In the second example that I have, that was an example of rationalizing the numerator. Here's an example of where you'd need to rationalize the denominator. So we're going to approach 1 this time, and we have x minus 1 over the square root of x minus 1. So if I try to plug in 1, you'll notice right off the bat that you'll get 0 over 0, which is a problem. So then we have to do our algebraic method. Whenever there's a root, you are going to rationalize. This time it's the denominator. So I'm going to multiply by the square root of x, and since this is a minus, then I'm going to have plus 1 on the top and bottom. So I get the square root of x plus 1, top and bottom. Same thing. So now you're going to distribute it out. You're going to FOIL. So I'm going to FOIL this to this. And so when I multiply it out, sorry, my pen's having problems here. I multiply the top and I get x root x And for this one, actually, you know what, I'm going to leave it not foiled out for right now because I really care about the bottom. I'm just going to leave it as x minus 1 for right now, and I'll foil it out in a minute. Times the square root of x plus 1. All over, when I FOIL this out, I end up getting x, and then I get plus root x and minus root x, which cancel, and then minus 1. And then I end up having that. So notice how the x minus 1's cancel out. So now I can go ahead and try to plug in 1. So when I go ahead and try to plug in 1, I get the square root of 1 plus 1, which is equal to 2. So my little hint is to, wherever you rationalize, multiply these out first. Don't FOIL the other part out, because something will probably end up canceling. So the last part of the notes is going to review some of the concepts that we did in today's lesson. The limit of f of x as x approaches a exists, so I'm reading right down here, if and only if the limit from the right equals the limit from the left. So if these two are equal to one another, then the limit will actually exist. Now what you're going to be doing is, algebraically, you're going to want to prove if the limit exists by looking at the graphs. So what you need to do to prove these is you need to sketch a graph. This is going to be how you're going to prove it. Because what you're going to be doing with the graph is you are going to be comparing or looking at the graph from the right and from the left to see if they're the same. If they're the same, then the limit exists. If they're not, it doesn't. So going into the first example, I want you to prove that the limit as x approaches 0 of the absolute value of x over x doesn't exist. Now you would think that you would have to use a calculator to do this, but you could graph this just by doing an old school XY chart. So if I plug in 1, I get 1. If I plug in 2, I get 1. If I plug in 3, I get 1. If I plug in negative 1, I end up getting, I believe, negative 1. Negative 2 is negative 1. Negative 3 is negative 1. 0 is undefined. There's an error. So when I go ahead and make my sketch, here's what ends up happening. Here's 1 and here's negative 1. That's the only thing that's going to happen in the table. So at 0, it's undefined, so I'm going to have an open circle. And when I plugged in 1, I had 1, 2, I had 1. Anything above 1 is always 1, and below negative 1 is always this. And open circles for both. So what you want to do to prove that it doesn't exist is you have to compare the limits from the right and of, we'll call this of absolute value of x over x, and you have to compare it to the limit as x approaches 0 from the left, or from the negatives of the same graph. So basically, if I'm going to be comparing it from the right, as I come in from the positives, the limit is 1, but as I'm coming in from the negatives, the limit is negative 1. So because these are not the same, you would say, therefore, it does not exist. They're not equal. So another quick example would be if I had the limit as x approaches 7 of f of x. I want you to tell me if it exists. So I'm going to say, does it exist? And here's what f of x is. It's a piecewise function, which we had today, so I'm going to go over the graph pretty quickly. And then the second piece is 28 minus 4x. So if you make your table and you go ahead and sketch a graph, you'll be able to compare the right and the left limits. So after sketching a graph, you would get something similar to this. And again, you'd be making your table and doing this on your own. The first piece is the square root. And the square root will look like this. It doesn't equal 7, and you get this from the table. And then the second piece is a line for x values less than 7, and I believe it looks something like this. Okay, So now to see if it exists, I should have put exist, you need to compare what's the limit approaching 7 from the right, or from the positives. What's that? And what's the limit as x approaches 7 from the negatives? If they're the same, it exists. If they're different, it doesn't exist. So if I go ahead and come in from the positives, so I approach 7 from the positives, I end up getting 0. If I approach 7 from the negative side, I also get 0. So you'd say, therefore, the limit as x approaches 7 of f of x is 0, because of the fact that those were the same. Alright, so I will see you guys tomorrow, and have a good night. So we're continuing on with section 12-2, and we're going to go over 8 limit laws. So the first limit law is the limit as x approaches a, and then we're going to go ahead and add them together. So it'll be f of x plus g of x can actually be simplified. So the sum, or the limit of a sum, is the sum of the limits separately. So it's the same as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So the limit of a sum is the same as the sum of the limits separately. That's the first law. Second law. The limit as x approaches a, so of f of x minus g of x, is the same as above, so this one is a difference. So the limit of a difference is the difference of the two separate limits. So it's the same as the limit as x approaches a of f of x minus the limit as x approaches a of g of x. So you can subtract the two limits separately if it's the limit of each of these together. Alright, number 3. Okay, so we have a limit as x approaches a. This time we're going to multiply a constant times a function, so c times f of x. So a constant times a function, the limit is the constant times the limit of the function. So we can pull out that number, the constant, and then we can just multiply it by the limit as x approaches a of the function f of x. So you can just take it out. Alright, number 4. The limit of a product. So we're going to do product. So the limit as x approaches a of f of x times g of x. You can probably guess what it's going to be. So you can break them apart into two separate things. You can take the limit as x approaches a of f of x times the limit as x approaches a of g of x. So you can basically take the limit of each of the functions separately and then multiply them together. So the limit of the product is the product of the limits. Alright, I'm going to erase this and go on to the last 4. So number 5. The limit of a quotient. So since we did product, we're going to do quotient. So the limit as x approaches a of f of x over g of x is equal to the quotients of the limits. So we can take the limits of each separately. So I guess I should have put parentheses around this. So it equals the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, the denominator. There is one little condition. The denominator can't be 0, so that limit can't be 0. So I'm going to say can't equal 0, that limit. Otherwise, it's undefined. Alright, so for number 6, I'll change it back to black. It's the limit of a power, is the power of the limit. So I have a limit as x approaches a of f of x raised to the nth power. That is equal to the limit as x approaches a of f of x, so you can find the limit, and then what you can do after you find the limit is raise that number to that power. So that's the same. So the limit of a power is the power of the limit. Alright, number 7. The limit of a root is the root of the limit. So this is what this looks like. The limit as x approaches a of the nth root of f of x is the same thing as taking the limit of f of x. So the limit as x approaches a of f of x, and then taking the nth root of that. So that could be square root, cube root, or whatever. So you find the limit, then take the root. Alright, then the last one, I think I can fit it down here. The limit of a constant is always the constant. So if I just have like a number 5 or 7 or 12 or negative 5, the limit as x approaches a of just a number is always equal to that number. So in this example, we're going to use the limit laws in this graph to help us evaluate each of these. So the first one is the limit as x approaches negative 2 of twice f of x minus g of x. So we're going to go ahead and simplify these a little bit. So we're going to first do twice f of x right here. This is the same thing as, I believe, number 3, limit law number 3. A constant times, the limit of a constant times a function is the constant times the limit of the function. So this is the same thing as 2 times the limit as x approaches negative 2 of f of x. And then minus, and then we're going to use the second one, the difference, the limit as x approaches negative 2 of g of x. And so we're going to go ahead and use the graph to find that. So f of x is the one in red here. So as x approaches negative 2, so here's negative 2 right here. As x approaches negative 2 from each direction, the y value is 1. So I'm going to get twice 1 minus, and then as x approaches negative 2 of g of x, that's this second one, from the left and from the right, it looks like it's going to be negative 1. So I get minus a negative 1. And when I go ahead and simplify that, I end up getting the limit as 3. Alright, the second example that I have is the limit as x approaches 1 of f of x squared. Okay, so what we can do is we can go ahead and find the limit as x approaches, right, I guess we can find the limit as x approaches 1. So let me erase on the drawing, so these will be gone. And we want to approach 1 on f of x, and then we're going to square that answer. So I will come in towards 1. So here's f of x, the one in red. So when I come towards the right from the left, it's it looks like it's 2, and then I come in from the right, it's 2 as I approach 1. So the limit is 2, and then I just get 2 squared, which is 4. So my third example, I have the limit as x approaches 3 of f of x over g of x. So we can calculate the limits separately. This is the same thing as the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x. And this will work as long as g of x doesn't equal 0. So using the graph, here's 3. So here's 3. Now remember, f of x is the one in red, so as I approach 3 from the left, it looks like it's about a half. And when I approach, when I approach 3, we're going to 3, it looks like it's 0 from either direction. So I end up getting 0. And then when I approach 3 on g of x is approaching 3 in this direction. So here's 3. It looks like it's going to approach 1 from this direction and this direction. So it looks like the limit is 1. And that would just be 0. It's not undefined because the denominator isn't equal to 0. And in my last example, I have the limit as x approaches 1 of f of x times g of x. So we can go ahead and calculate the limits separately and then just multiply them together. Because if you remember the limit law, this is the same as the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. And we can just multiply the two values together. So here's 1 again. F of x is the one in red, so as I approach 1 from the negatives, it looks like it's 2, and from the positive, it's 2. So I get 2 times, and then as x approaches 1 from the negatives on g, it looks like it goes to negative 2, but when I approach 1 from the positives, it looks like it goes to 1. And because these don't connect, or they go to two different values, this does not exist. They went to the same number, it would. So basically, the limit isn't possible. It does not exist. So you can't multiply one that does and one that doesn't. So here's the last example, and I'm actually going to give you problems to do and bring these to class, and we'll go over them tomorrow in class. I want to see if you guys can do these. So the goal is to evaluate by direct substitution. Alright, so this is me checking your understanding so far. So I'm going to be asking for these tomorrow, and again, I will go over them. So the first one I want you to find is the limit as x approaches 2 of x squared plus 6x over x to the 4th plus 3. That's x to the 4th plus 3. Alright, and I want these all done algebraically, if possible. Alright, second one. I want you to find the limit as x approaches 4 of x minus 4 over x squared minus 16. Third one, I want you to find the limit as x approaches 10 of just 3. It's one of our limit laws today. So find the first two algebraically, and then number 3, use one of our limit laws from today. So I will see you tomorrow.